stuff that we've learned, and that's going to be kind of what we're going to do for the remainder of the semester, is just focus on various applications of the counting techniques we've learned. So we're going to start by dealing with the Erdős distinct distances problem and using pigeonholing to get some non-trivial results. So, given a set, let's say a large finite set of n points in the plane, they determine at least n to the 1/2 distinct distances. This here is asymptotic notation, so I'm saying at least n to the 1/2 distinct distances where I'm ignoring possible multiplicative constants. And since I've said large, I'm looking for n large. So we're not talking about n as 1, 2, or 3, but n is maybe billions or trillions. We can be more precise with this if we use notation like big O or big omega. So basically, just as an aside, I'll say f of n is squiggly less than g of n is logically equivalent to f of n is big O of g of n. If we have it go the other way, then we'd have big omega. And if we have squiggly equals, then that means that f of n is squiggly less than g of n, and g of n is squiggly less than f of n. This is f of n is squiggly equal to g of n. So it's just a slightly different notation for big O. So let's prove this theorem, and this is due to Erdős in 1946. And this is the distinct distances problem. So, proof. What we're going to do is we're going to fix the point that determines the most distinct distances. And actually what I want to do, I want to be a little bit careful here. I want to say fix a point that determines the most distinct distances, because there could be more than one. Call this point P, and the number of distances T. Now what I'm going to do is I'm going to draw T circles centered at P, covering the other points. So the idea is I've got some finite number of points. What I've done is I've picked the point that happens to have the most number of circles required to cover the other points. But there could be other points that determine the same number, but in particular, I've picked one and I've called it P. That's P. All right. So now what I'm going to do is I'm going to fix the circle centered at P with the most points from our set. So in this case, we've got whatever circle centered at P, and we're going to suppose that it's this one. All right? We're going to call it C. Now, by the pigeonhole principle, we must have at least n over t points on C. So why is that? Well, I've got t circles, And each point, aside from P, is on exactly one circle centered at P. Well, so I've got n things, and I'm putting, well, n minus 1 things, and I'm putting them into T distinct boxes. So that's roughly n over T, and that's why I've got this squiggle here. So it would technically be ceiling of n minus 1 over T. But we're going to try to avoid getting bogged down by details like that. So we're just looking for asymptotic results for now. So by the pigeonhole principle, we must have at least this many points on C. And now here's what I'm going to do. Again, by the pigeonhole principle, either the top or bottom half of C has more points. Again, we're pigeonholing here. We've got some number of points. I shouldn't say has more points. Has, let me be specific, has squiggly greater than n over T points. So again, it should have squiggly greater than n over 2t points, but that 2 gets buried in the constant of this asymptotic notation. So what do I mean? I take C, I cut it in half. Either the top or the bottom has to have at least a constant times n over t points. And that's because we've got about n over t points on here. So they're either in the top half or in the bottom half. Well, one of those halves is going to have at least half of those points. Now, fix the leftmost point on the half with the most points. Well, I shouldn't say with the most. On a half, because they could both, it could be evenly split, but on one of the halves, on a half with squiggly greater than n over t points. And notice that all distances between it and other points in that semicircle are distinct. What do I mean? So let's just, in this case, let's suppose that the top half had at least half the points. I'll pick the leftmost point here, and now let me draw circles centered at this point, covering the rest of the points. Well, we notice that these circles are going to be hitting each point on this same half at most once, right? So if I draw these covering circles, maybe there's a point down here, so I've got to draw a covering circle like this. But if I'm just focusing on the points for the top half, then I'm ignoring that. So I'm drawing these covering circles to cover the points in the top half, and I notice that all of these have to be distinct. And why is that? Well, that's because two distinct circles can intersect in at most 2 points. So if I have a circle centered at this point, and remember this circle is centered at P, those circles can intersect at most twice. So that means each of these circles are different radii because they have the same center, which means I've got roughly n over t distinct distances measured to this point. Okay, so let me recap the information that I have, because, well, I guess I could probably just squish down like this. So to recap, we have at least t distinct distances to the point P, and at least n over t distinct distances to, let's call this point L. No, let's call this point Q. This leftmost point, fix the leftmost point, which we will call Q. So I've got at least t distinct distances and at least n over t distinct distances. So how many distinct distances do I have? Well, number of distinct distances if I count this, the number of distinct distances is bounded below by t, and it's also bounded below by n over t, which means the number of distinct distances squared is bounded below by t times n over t. So I've used each of these. Well, these t's cancel, and this tells me number of distinct distances is bounded below by n to the 1/2. And that's the end of the proof. Okay, what did we do here? I had the square of the number of distinct distances was bounded below by n, which means take the square root of both sides. Number of distinct distances is bounded below by n to the 1/2. Again, ignoring some constants. So let's roll the whole proof back just from the start. What did we do? Well, we took a point that had the most distinct distances measured to it, drew circles around it, and picked the heaviest circle. Heaviest meaning, one of the circles with the most points. So by the pigeonhole principle, it had to have at least n over t points on it. Then we looked at that circle, we cut it in half, picked the half with the most points on it, or a half with at least constant times n over t points on it. And then we drew circles centered at the leftmost point on that semicircle. And we noticed that each of these semicircles had to be a different radius, meaning that they all are distinct distance to q, all the circles on this semicircle. So that means we have at least a constant times n over t distinct distances measured to q, and by construction we have at least t distinct distances measured to p, again ignoring constants, multiplicative constants. Putting those two together gave us that we had at least square root of n distinct distances. Okay, that's great. Let's now prove the same result again using a slightly different proof, or a slightly different explanation of what I would call roughly the same proof. So pick 2 points, P and Q, and draw covering circles centered at each of them. S at P, T at Q. So we have S circles centered at P, T circles centered at Q. Okay, these are circles. Don't worry about how ugly they look. Now, if these are all the circles to cover all the points, what's that mean? Well, again, any point has to live on an intersection of two circles, right? I can't have a point that's just out here on its own because it has to be on a circle centered at P and on a circle centered at Q, right? So all n minus 2, which is roughly n, points live on the intersections of these circles. So it might be useful to know how many such intersections there are. Well, for sure, if I have S circles centered at P and T circles centered at Q, I don't know if every circle will intersect with every other circle, but for sure the number of intersections is going to be bounded above by S times T times 2, because each pair of circles can intersect at most twice, and there are ST pairs of circles. So the number of intersections is bounded above by 2ST, right? For each of these S circles, it could intersect each of those T circles at most twice. Maybe I have two circles touch at a single point, I don't know. But no circle centered at P can intersect with another circle centered at P. Same for Q, which means the intersections between circles are all circles centered at P intersecting with circles centered at Q. All right, great. So now, I said that the number of intersections is no more than 2ST, but the number of points is no more than the number of intersections, which means we have that n is squiggly less than. I mean, if I was being really careful, I would say n minus 2. But I'm intentionally trying to get away from worrying about some of these lower order terms because they can get in the way of the main idea. N is squiggly less than the number of intersections of these two circles, which is less than or equal to 2st. Putting these together, so ignoring the multiplicative constant here, I have that n is less than or equal to st, squiggly less than or equal to. Now, without loss of generality, suppose s is less than or equal to t. Well, that means that n is less than or equal to st, which is less than or equal to, well, if s is less than or equal to t, this is less than or equal to t squared, which means t is squiggly bounded below by, t squared is squiggly bounded below by n, which means t is squiggly bounded below by n to the 1/2. And we're done again, because for whichever point, I said s circles at p, t circles at q. Without loss of generality, s is less than t, but if we switched here, whichever point has more circles, that number of circles is t, and we notice that each of these circles is a distinct distance, right? So each circle is a distinct distance measured to its center. So when I say that t is bigger than n, that means that there are at least, when I say t is bigger than root n, that means there are at least root n circles measured to q. Now again, this is without loss of generality, so if this wasn't true, then we'd just change what we need to change. But that's the crux of it, is the number of distinct circles required to cover the other points gives us a bound, not an exact count, but it gives us a bound on the number of distinct distances. So I claim this is roughly the same argument. The question is, where was the pigeonholing? Okay, so I want you to think about that, and we'll do some more stuff along these lines through the rest of the semester.